No, we're here with the Godfather. The Godfather. So Bruce, can you introduce yourself?
Yeah, I'm Bruce Bugbee. I'm a professor at Utah State University, and I've now celebrated my 40th year of teaching and research at Utah State. Uh, and I also have a little side business called Apogee Instruments that makes lots of radiation sensors.
Nice. We're here also with Roach
Yep. What's going on? How's everybody doing?
and Morgan.
Hey, what's up?
Bruce, what R&D projects are you working on right now?
We have three big projects, and I guess given the 40-year career I talked about, I've actually got more funding and more students right now than I've ever had. So it's a pretty active time.
Do you think that's because of the cannabis industry?
No.
Okay.
It is partly because of that. It's my whole career I've gotten funding from NASA, competitive grants, usually in 3-year packets. And that stuff is all to feed people in space, grow food for people in space in a very controlled, regenerative environment. And in NASA's case, you can't just build a greenhouse on Mars or the moon because there's no atmosphere. The meteorites would smash it. So you have to have it real protected. And that means electric lights. And now with LEDs coming along, wow, that really made food production a lot better.
So you're having a lot of inspiration from like SpaceX and guys that want to.
Yeah. And in my case, that started in the early 1980s when I first got funding from them. And back then there were no LEDs. They were way out in the future. We were all using metal halide, high pressure sodium, and all the research we did on that was with filters. We took the lights and put all kinds of theatrical filters in there
to get different color
to create
spectrums.
these spectras.
Yeah.
And so some of those papers are a long time ago, but they're now being cited.
What projects are you working right now on with NASA?
The big one is called the CUBES project, and that stands for Center for the Utilization of Bioengineering in Space. And most of the people in that group are working on microbial transformations of things to recycle waste back into something usable. For example, one group is working on microbes that can make a type of a polymer that we can use in 3D printers to print a microbial product that we put in 3D printers and print things out of it. So it's a microbial-based plastic, for example.
Now they're doing this with plants, or they're doing this in the soil, or how?
No, the microbes grow in a bioreactor.
Okay.
And it's a controlled condition. But they change the environment, so they make these polymers. They're like a plastic polymer.
Nice.
That's one group in this. That NASA specifically wanted additional research on higher plants for food. And as you can quickly see, they're making plenty of purified water for the people. They're recycling waste. We put all the waste right back in the root zone after appropriate composting. And they also produce all the oxygen that people need. So this is a sealed thing with plants in it.
Yeah, that's awesome.
That's the NASA-funded work.
Yeah, that's awesome. You're also working with the USDA on some stuff?
Then we hit on another big grant with the USDA, and this one is called the LAMP project, LAMP, Lighting Approaches to Maximize Profits. So as the acronym sounds, it's way more applied. How do we help growers optimize lighting to maximize profits? And we wrote it that way on purpose because it includes supplemental light in greenhouses and indoor agriculture. Both places use a lot of lights. So that's a lot of the same goals as NASA, but way more immediately applied on Earth.
Yeah, right away. Have you seen a large uptick in the last 5 to 10 years on cannabis cultivation as far as taking some of your time?
Yes.
Research.
Because we had a reputation for doing controlled environment research, growers were anxious to fund us to help them with cannabis cultivation. And this was several years ago, before it was federally legal. But the minute low THC cannabis became federally legal, then we could take their money, and we started doing research on cannabis almost literally the next day.
Low THC cannabis.
And this was all, the license was for low
Yeah.
THC cannabis. And so we got a big jump start because we'd been doing so much of this controlled research before that. So cannabis is now a big part of the lab. Like a third of the funding comes for cannabis cultivation.
No, that's huge.
High THC as well.
Well, good question. Our license is only to do low THC cannabis, but low THC and high THC cannabis are only separated by one gene. And so it's like field corn and sweet corn. They're only separated by one gene. So we do research on low THC and extrapolate to high THC. Which works pretty well for most things, but when you get in the nuances of quality, then there's some differences.
Got it.
You could lose federal funding if you do higher than...
Yeah, I think NASA wouldn't be happy if we started, the word got out, we were studying high THC cannabis. They might get sideways with the president or something, and NASA would get all its funding cut. Or I don't want to be responsible for that.
Yeah.
But what you learn by working with NASA and USDA, it applies. It translates to these controlled environments people are working in now.
Directly applies. Yeah, NASA is all food crops. Although I guess we could tell them we got to grow hemp for fiber. We got to make clothes for these astronauts. So.
Need some high THC up there too.
Yeah. Oh, but accidentally that fiber.
I'm waiting.
We want it dual purpose, right?
Yeah.
Slip a few in.
Yeah. Wear it, smoke it.
You're also a business owner and have 40 employees. Can you talk about that?
Yeah, that sort of started accidentally almost. I was making light meters just on my kitchen table. I converted voltmeters into put photodiodes in the top, and I built them for my laboratory. And I built quite a few. And then visiting scientists would come and they'd see these and they'd go, "Oh my God, this is terrific. Could you make one for me?" Well, they were friends, and sure. So I started making some more. And then pretty soon people started calling me up and saying, "You don't know me, but I want to buy one of your meters." And then so I started Apogee to make these. And people say it started in my garage, but it really started at my kitchen table.
So Bruce, that requires understanding of semiconductors and silicon photodiodes and electronics. I mean, that's a little bit of a different skill set than your normal work, and I think that translates to LEDs as well, and understanding the physics behind there. So can you give a little background about your interest and your expertise in that?
Yeah, I started school in engineering. I was good at math in high school, and I would become an engineer. So I started studying engineering. Mostly it was mechanical, but some electrical. And then engineering was following all the rules and doing fixed stuff. And I took some biology classes, and I thought, wow, these people need help. I mean, this is really complicated. But to me, biology was science, and engineering was following the rules and repeatedly doing things. And so the science part of biology was just fascinating, and I switched to biology. But my engineering background helped a lot because I could do a real quantitative biology because of that.
Yeah, we've been doing a little R&D ourselves, with Morgan, and we learned a lot. We learned red light, plants like red light. And especially in a vegetative state, we've seen some big significant differences. What have you seen in your lab with using red light?
Well, for starters, from an engineering standpoint, that's a really efficient LED color. And because photosynthesis is driven by number of photons and not by energy, the longer the wavelength photons, the more efficient they are. So red is longer than green, green's longer than blue. So just from the pure physics of it, going to a longer wavelength photon gives you more photons with the same amount of electricity, which is a big part of the reason they're so efficient. But in addition to that, well, red is the opposite color to green. So it's really well absorbed by plant leaves, and it really, per photon, it's because it's well absorbed, it results in a lot of photosynthesis, and that results in a lot of plant growth. So not only is it efficient from an electrical standpoint, but it's really efficient from a physiological standpoint in all green organisms, algae, plants, everything. They have just absorbed those photons really well.
So that's why we're seeing, with our veg lights. I mean, as cultivators growing up in the cannabis industry for so long, we've always been using blue light. And now that we've done all these testings, we're seeing it's the opposite. What's your thoughts on blue light with veg, and why do you think cultivators have been using it for so long?
Many years ago, I don't know, 15 years ago, everybody was metal halide for veg, high pressure sodium for reproduction, flowering. And, well, why do you do that? Well, I don't know, everybody does it. That was always the answer. Until one day I realized, well, the high blue light from metal halide keeps the plants compact and short, and that's really what you want to have. And then after they're flowering, you can use more efficient high-pressure sodiums because they're making flowers now. They're not going to get too tall. So I think it was the observation that metal halide helped keep those plants compact in veg, and then they could use the more efficient high-pressure sodium later. I'd never heard anybody say that was because of high blue, but now we know that's true, now that we can manipulate spectra. So blue photons are terrific for keeping plants compact.
We've tested the three main spectrums that we're releasing at Luxx. We're doing the 80R and the 90R, which is 90% red and 80% red. But compared to the 90R keeps the plant a lot shorter, stockier, compared to the 80R and metal halide. So it's like that high red is getting even a shorter, stockier plant. Why do you think that is?
The first thing I would look at carefully is the intensity of light, the total photon flux. You call it 90R?
Yeah,
or R90?
90% red.
Yeah. Since that'd be a little more efficient, that means the photon flux is a little higher for the same watts of input energy. So high intensity light also keeps plants shorter.
Oh.
But we just looked at that, and with our prototypes, they're pretty close to the same PPFD, but a little bit counterintuitively, the 90R has higher blue than the 80R.
Yes.
And the
Okay.
80R...
You didn't tell me that.
That's the trick question.
Hey,
We went over it earlier. This was right before you got there. We were looking at them, and we were going back and forth on that, right?
Yeah.
So they do have a higher percentage of blue, which actually directly goes with what he's saying, right?
So what percentage greater?
So the
than this?
80R has less blue. than the
80R
90.
is like 7% blue, and the 90R is 10% blue.
Yeah.
And then the other side of the story is that blue LEDs should be more efficient than white, but just because of the economics of LED production, the white LEDs are the same efficiency, same efficacy as the blues, because they use the best underlying LEDs in the whites. So they end up being really close to the same performance. Our 90% R90 fixtures like 3.15, and our 80% like 3.05 micromoles per joule. Both exceptional, but not as big of a drop off as you might think.
Do you think there's a place for blue light in indoor cannabis cultivation, as far as like metal halide?
Well, you could use metal halide to get some blue, but I
Yeah.
think that where we're headed is all LED fixtures, just because they're so much more efficient
Yeah.
than metal halide. Yeah, I mean, you could ask the question, why don't we use 100% red? And the first thing I would say was, well, then it's hard to see the plants. There's no green at all. But I don't know. Let's say you have a headlamp or something, and that's not an issue. We've done studies on minimum blue light, blue photons, and we've done them. That was mostly with NASA funding, with lettuce, soybeans, wheat, other kinds of cucumbers, other kinds of crops. But when we've done them on cannabis, they do get taller, but if the intensity is high enough, they don't become unmanageable tall. And that's with zero blue.
Wow.
So now a little bit of blue helps keep them short. And that's sort of risky territory to not have any blue at all.
Yeah.
But the plants grew fine with no blue at all.
You just have to have the intensity there.
You just have to have the intensity.
Got it.
Yeah.
And you also just put out a paper talking about color rendering of these horticultural fixtures. And I think that's pretty important and doesn't get discussed enough. Do you want to just mention that a little bit?
Yeah. I think that was a NASA technical memo. If
This guy reads all kinds of shit.
No,
it was,
yeah.
but we did put out a paper, and I can't remember where it's published, but it's open access anyway. Years ago, we told people, quit thinking about foot candles. That's only for people. That's a bad metric. Just forget about it. Well, that led to purple fixtures, blues and reds, and you can't diagnose your plants. You can't tell if they have subtle nutritional disorders. You can't tell if there's microscopic insects. You got to have some green in there. And we've seen this directly. We did a study. It got some spider mites, and under the high pressure sodium, we just didn't see them. But under LEDs with more green, with a better color rendering index, we saw them right away. And man, that's pretty important to be able to diagnose those subtle disorders. So now color rendering index becomes a big deal in fixtures. And I think your new fixture is a pretty high.
Yeah. That was one of our design rules with the new fixtures. We needed to be able to work under them. I mean, and there are different settings, which is why we brought in the R90, the blue and red fixture as well, because there's different settings where it's, maybe in a stacked setting it's okay. You can have the blue and red and have your aisles be white or something like that. But the R80 it has good color quality for people. And that was one of our targets in the development there.
Isn't that a RF50? I think, and that
the color fidelity index is like
maybe
50. I think it's 50, and the CRI is like 40. We were talking about that.
Yeah, we were. It's the specs on your fixture, but Morgan and I were talking about it. I think the old metric CRI was 44, and by the new improved metric,
it's like 50.
It's 50, which is very adequate. High pressure, it's better than high pressure sodium.
How are you liking the specs of our new lights?
Oh, it's great. We wrote a paper with Morgan and I and one of my really excellent graduate students a while back, and we said, here's the spectrum we think would be ideal. Well, that's pretty close to the spectrum you have.
Yeah, that was really close.
Yeah, that was the process. We brought at Luxx was, okay, these are the new guidelines. This is the new understanding. LEDs are the new technology. What can we do with that? And we followed that kind of playbook, and we had to throw them over the wall to Roach and Ivan and see how things really worked out. And there's some trials and tribulations, but it's worked out pretty well.
Yeah, no, 100%. Why is it that these high red spectrums in the flower rim bleach out all the tops of the nugs?
We would really like to know the answer to that. So the whole planet right now would like to figure that out. So we've had some pretty sophisticated and detailed discussions with other physiologists of what's going on. And the short answer is we don't know. But the more detailed answer is that doesn't keep us from making hypotheses about
Theories.
what might be going on. And my personal thinking is it's happening in the cells in the meristem of a young flower way before they come out and show in the top. It's not like they come out green and they go white. If you watch them carefully, they come out white.
Yep.
So that means those cells didn't have chlorophyll 2 or 3 weeks previous, and then they just multiplied and they came out to the top.
At the cellular level.
Yep, at the cellular level.
Yeah.
Yep.
They're getting bleached.
Mm-hmm.
Yeah.
And it's a remarkable thing. We had not seen this in any other plants because it's not, we call that chlorotic when there's less chlorophyll. It's yellow. These are not chlorotic, they're white. There's no chlorophyll at all. And it's an intensity multiplied by a spectral effect.
It's kind of like too much of a good thing. Maybe.
Yeah.
Plant can't reproduce itself fast enough to let the color keep up.
Yeah.
It almost seems like.
Sort of, yes. It could
when it's
be,
young, because it's in
except-
such an explosive growth. It's
Yeah.
happening so fast. You're putting so much red on it, and it's just like, I can't.
But now, Roach, when we get into this, then you say, well, if that's the case, doesn't it happen with all colors? No, it has to be high red.
Yeah.
Yeah. it only
And
happens.
if we had less red, we give them really bright light, it wouldn't happen.
Yep.
It's really interesting. It has to be high light and high red both. So those two numbers together are a fraction of a daily light integral of just red. That's above some number, you get white tips. I will say there's a lot of interactions with genetics. If we're going to breed things, I think we can genetically select away from it.
We've seen that too.
Yeah, we've seen that. We
Yeah.
run hundreds of strains, and we'll see ones that are more sensitive to light than others.
Yeah. But
We've
it's a
seen
big...
stuff- We've
it's a-
seen certain strains go
Yeah.
bleach under a HPS light. Nothing even
Yeah.
crazy high intensity. Just certain genetics do that.
Yeah.
What's the number that you're seeing in your labs that you're seeing that bleaching?
For
The percentage.
It's not so much the percentage. I would say it's
The DLI, huh?
if we give above a DLI of about 600 micromoles per meter squared per second of red, we start to see it. And then if it gets more than that, we see it more. And again, this is with a 12-hour photo period. So certainly 1,000 micromoles with an 80% red would give you 800 micromoles of red, which would be plenty to see it.
Yeah.
So
That's an approximate number, but it gives you the concept of what's the threshold of red photons.
we'll have to check that out because we stepped down the red percentage when we were doing this development to see where the bleaching was initiated, and definitely it was
55%.
yeah, that was like conservative, and it depends on the cultivar.
It was even happening even that low at some bleaching.
Yeah.
Yeah, we're testing it in a greenhouse right now. I'm interested to see how the daylight and that Spectrum 3 works, because if you use Spectrum 3,
It's the 80.
the 80.
Yeah.
Oh, sorry.
Yep.
Yeah, Spectrum 3 to us, but 80
R80.
R80 in a greenhouse or in an indoor environment, you'll bleach out your whole entire flower room. But in a greenhouse environment where I'm testing it at my greenhouse right now in Nevada, we'll see how it does with the mixed sunlight.
Yes, that's yeah.
What do you think?
Let me know how you find out.
Yeah, so I'm interested to
Yeah,
see.
if my theory of threshold of 600 holds, it doesn't matter where those 600 come from. They could be from sunlight.
Exactly. That's what.
So
That's what
I was going to
Morgan-
calculate it out, for winter when you're using max supplemental light, and the normal spectrum and the DLI for daylight, and the red DLI for daylight, and so run the numbers and see where we end up, and then Brandon can put his crops at risk.
Yeah, it's fine. I mean,
It's been a relatively recent thing when people started using a higher fraction of red like you are and higher light both. All of a sudden, oh shit,
Yep.
we give something. This is
Well, because they're pretty directly related too, right? You know, higher percentage of red, higher
yeah.
light, because they're so efficient.
both of those.
Yeah.
Yep.
Yeah.
So we're talking about red, and let's go into UV, the other opposite of the spectrum. Are you studying a lot on UV right now?
We are, and especially in the cannabis world, the conventional wisdom is that you can increase cannabinoids and increase THC by giving UV photons. And it's based on almost exclusively on a paper by a guy named Leiden. It's Leiden and somebody else who studied it like 25 years ago. And they were looking at sunburn protection from the sun, because cannabinoids absorb UV and they can protect a plant against sunburn. And so they were only doing leaves of plants. But in one of their cultivars, they gave it more UV and it made more cannabinoids in the leaves. And the other cultivar, it didn't happen. And so lots of people have said, well, Leiden has proven that high UV makes cannabinoids go up. And if you read Leiden's paper, in the last sentence of the abstract, he says, so the effect of UV is equivocal. Now you look up equivocal, and it means uncertain. We don't know if it does anything.
It happened once. We don't know if it was,
But everybody cites that paper, and they said, Leiden shows it helps. Well, maybe it does. So we've done a series of studies with UV, different doses at different time intervals. And so far, we've not been able to show that UV increases cannabinoids in the flowers.
That paper, it was UVB too, just to be clear.
Right.
It wasn't UVA. So that means you got to find a UV source that's like 320 nanometers. That's the sunburn portion of the UV spectrum, not the black light portion of the spectrum.
And when we did our research on the UV part, we used a UVB fluorescent light. We didn't have UVB LEDs at the time. But
we made you some.
But now we do,
got you
because
some,
you got us some. Yeah. So the
Yeah,
UV
some are
LEDs
expensive.
are more narrow.
Those are some expensive lights.
Yeah, they're more narrow, but in general, we haven't found the effect that we thought we would. And the concept is cannabinoids are what we call secondary metabolism. The plant doesn't have to make them; it just makes them as a supplemental compound. And UV light triggers secondary metabolism, like you can make green lettuce turn red with UV. And that's secondary metabolism. My phone's going
That's what happens
off.
when you're a business owner.
Yeah,
That's what. Yeah.
it stopped. Thanks.
You're good.
They gave up. They give up quickly on me. 2 rings and
So
gone.
did you look at? So you said you did UVB. Did you look at UVA then as well?
we did. Yeah, that didn't help either.
How long have you been looking at UV?
Oh, I don't know, a year,
Year?
a little over a year
You
maybe.
find out a lot in a year.
Well, yeah, if you stay focused on it and grow crops, yeah. Morgan, the UVA that we're using was LEDs at 390 and 380 because they're still quite efficient.
Yeah.
So it was
We've-
almost visible.
We've made some test bars at 395 and some 385 bars are in on the way. So we're gonna look at have that as a tool to check that out. But based on what you've been telling me and what you're saying right now, it's maybe a little bit marginal. And then taking it to the next level, trying to apply it at scale, it might even just be that much more difficult when you could do other things like increase your red or
Yeah.
have other knobs to turn.
There's 2 different ways of testing. You have steady state and pulse UV, right?
Yeah. Pulsed might mean very high frequency, but sort of phasic. Give them just for an hour a day.
Or or every other day or once a week,
Yeah.
or so.
Or the 2 days before you harvest too.
Yeah. Have you done that?
No.
Okay.
Yeah.
Some
We did time intervals, but only continuously through the flowering stage.
Yeah, we plan on doing that.
Yeah, we have another another concept we're gonna try out we call them booster bars, booster bars to just kind of blow out a certain spectrum at a certain time in the growth process. So it's like a little blast of light. It's just to see how that works.
Mm-hmm. It's interesting because in principle, in other species, this has worked.
Yeah.
So why isn't it happening in cannabis? And why didn't it happen even for Leiden?
Why did it take so long for cannabis? Because it's happening, I feel like, right? LEDs have come a long way.
No, you're talking UV maybe.
I mean the effects of UV on cannabinoid synthesis.
God,
we would think they should help.
Yeah.
Well, there's not enough. I mean, everything. There's no federal funding, so nobody's doing the work. You know, it's hard. It's hard to do the work. I mean,
but maybe you guys could answer this. I mean, genetics have been bred for higher cannabinoids since the 80s. Also, right?
No, for sure.
So maybe that impact that applied to a lower naturally producing cannabinoid plant. Now you have a higher naturally producing cannabinoid plant, and that effect is much more marginal and maybe in the noise pretty much.
It's tricky because UV light can also degrade cannabinoids.
Yeah.
So you don't want to give them too much.
Yeah. We were kind of talking about earlier too.
Yeah.
Yeah, talking about too much. I mean, do you think on an indoor environment cultivating cannabis, do you think there's a term which is too much PPFD?
Yeah, but I think it's higher than we've ever given the plants so far. It's remarkable in some of our studies, and not just our work, but other people's. We keep raising the intensity of the light, and the yield keeps going up. And in some of our highest studies, we were giving them 70 moles per meter squared per day, DLI of 70. That's more than they get outside in the field in the middle of the summer. Even if every day was a clear day, they still wouldn't get 70.
Have you seen a degradation in quality or maybe THC?
Yes. We as the yield goes up, this thing starts to occur called yield dilution, and the flower buds get bigger, but the cannabinoids don't go up in proportion to flower size. This doesn't always happen, but we've seen it, and other people have seen it as well. The percent THC goes down as the yield goes up. So as a tendency, we see that happening.
So you have more plant mass with less
concentrated THC. Yep.
So
yeah, it needs to go up together to be better, right? You have to size and cannabinoids to go up.
Yeah.
For
I mean, for Jungle Boys, right?
I mean, just for all cannabis.
I mean, for all cannabis.
For all cannabis, right?
Yeah.
Nobody wants to grow a bunch of big old boof sticks, I don't know.
You'd be surprised.
Make my shit frosty.
But as we were talking about earlier, Roach, it's flower color, it's flower shape, it's concentration.
The smells,
can
effects.
we get the yield up and have the exact same quality? And it's definitely difficult. It's like driving, your Tesla, 140 miles an hour versus 50.
What were you doing with this guy on the way here?
We got here fast.
We were doing a little research.
We're doing some research.
But it's an analogy. It'd be hard to go that fast and still be safe.
Yeah, you can't just be coming into you want to start your first grow. It's like you're just getting your license, bro. You've never driven a car before ever, and now you want to drive an F1 car. It's like you're going to crash it, right? So that's kind of the other thing when you start playing with these higher intensities, right?
Yeah, hard to keep everything in balance, yeah.
Everything happens a lot faster.
Yeah. But that part of it is the nutrition, the watering, the temperature, everything, so that you can drive it fast.
Yeah, and not crash.
And not crash.
Crop crashing. That's what we call that.
Maybe not exactly crashing, but denting your car. I mean, something undesirable.
If you can't sell your weed, it's a kind of a crash.
Yeah.
The economically, for like yield to energy usage, is there a sweet spot on PPFD to the canopy? that you've kind of?
Yeah, as a broad rule of thumb, I mean, 1,000 micromoles per meter square per second is a pretty nice rule of
1,000
thumb.
ppfd.
Yeah,
Yeah.
that's a nice round number. And the yield really, even yield and quality both are increasing up to about that number.
Yeah.
And now can we inch it higher than that? We definitely can for yield and quality. But if you was to pick a number, I'd say 1,000.
Yeah, that's what we like.
Yeah.
We like to see about
that right?
1,000. Yeah. 1,000's the number that we like to use in our gardens.
Mm-hmm.
On HPS, I was listening to a podcast that you did, and you said something about HPS compared to LEDs, and I don't know how long ago it was, but I think it was quite a while ago. And you said LEDs are 5 times more expensive than HPS. Do you think that's still true today?
Maybe. The economics are always hard to know because manufacturers give discounts on lights. And so if you look at list price, but then people don't, they buy in volume and they get discounts. And I've had people be real critical of me to say, my God, people get discounts on LEDs all the time. Well, they get discounts on HPS too.
Yeah.
Same thing. In quantity, you get discounts. But man, you get 1,000-watt HPS down or $250. Whoa, I mean, that is cheap. It's just amazing that one bulb carries 1,000 watts. And now do you replace that with 1,000 LEDs at 1 watt each? It's hard to do.
Oh yeah, to replace watt for watt and match price. Yeah, I could definitely see the 5 times.
Yeah.
But on PPFD output, or total output, I mean, to get 1,000-watt HPS, what is our 1,000-watt HPS? 1,900.
Yeah.
And then our 645 is 17 and some change.
Yeah, 16.
Similar.
Yeah, it's close.
Yeah, it's pretty close.
And a little more directed, so you get the same PPFD or better because you can put it closer to the canopy.
So
More average.
I should be asking you, is it still 5 times as much?
No, it's like 3.
Yeah.
We're probably like 3 right now.
Yeah. Okay.
Yeah, it's getting better. Just as not the red diodes, dude. The red diodes are so expensive.
But on a per output basis, they're not that bad. They're more expensive, but per PPF,
Tremendous.
Everything we're looking at right now is efficiency. Of course we want better quality, but with it we
pay the money.
efficiency is
No.
yeah.
It's I could not believe the price of those bars.
Those are the best LEDs in the world right now. I mean, they're 70% radiometric efficiency, which is nuts, and then the red, which means that you're getting more photons per watt on top of that, and then the plants like it the best. So you're getting like a win-win-win. And so they are newer products though, so they are more expensive, but we'll get some more players in there, and the price will levelize, I think, a little bit.
Yeah, coming from 1,000-watt metal halide and then going to a 400-watt LED. I mean, you're getting your money back.
That's great.
That's 600 watts.
Yeah. When I've run the numbers for payback for indoors, I mean, it can be 1 year
Yeah.
payback. It's really fast.
Especially in Los Angeles where your kilowatt hour is
Yeah.
like 20 cents or something like that.
Ooh, yeah. So it can be a really
Power's not
fast
cheap in
payback.
California. Yeah.
Mm-hmm.
Yeah.
Power's not cheap here.
HPS versus LED on a greenhouse. I have a 40,000 square foot greenhouse. Just put like 400 double-ended 1,000-watt Luxx HPSs in there. What do you think? You think LEDs there for greenhouse setting, or would you pick HPS?
No, I think we're going to move to LEDs in greenhouses. But the payback period, when I run the numbers, now we're more like 4 years instead of 1 year. Well, a 4-year payback for most business investments, that's a no-brainer. You do it right away. But in the world of cannabis, people say, I don't know what the market's going to look like. I want a 1-year payback.
But also for greenhouses not doing cannabis, that's a tough business, right? It's kind of a slog. So having the extra funds to outfit a greenhouse, although there's all these huge greenhouses coming in, like App Harvest or whatever, that I think are going to take things to the next level. But yeah, sorry.
Yeah. That's, I should qualify that, because cannabis in a greenhouse can pour on the light. They really run the lights a lot, which is where the LEDs, then they pay back, because you're saving a lot of electricity. But if you're going lettuce, oh Christ, you can grow lettuce at 500 micromoles just fine. At way less light. You need to far less supplemental light to grow stuff like leafy greens,
which extends the payback period, right?
Exactly.
Everything takes that much longer.
Now suddenly you're at maybe 12 or 14 year payback, and business owners are going, no, I'm going to stick with HPS.
Yeah, the HPS, I went with HPS just because we're working on a greenhouse light right now. It's not out yet. But also the spread from an HPS, I was able to cover an 8x8 area in a greenhouse and get pretty significant DLI increase for winter compared to what LED that I could use to do that. So
yeah.
Do you need the heat of the light at all out there where you're at? Does it ever get cold during the night where you're like, I got to turn this light on, give me some heat?
Yes.
Yeah. So that's also kind of a little bit of a benefit.
Factor.
Yeah.
Yeah, for sure. And I'm not worried about cooling because I'm using a wet wall.
Exactly.
So I'm not, cooling my HPSs, so it's not a big deal.
Yeah.
I personally
what footprint do you put them on?
8x8.
8x8. Yeah, because it's not the same as
No, I mean on an indoor you're like what, 4.5 by 5?
With the aisle space, like 4.5 by 6.
Yeah, so 4.5 by 6. I'm 8x8.
4 linear,
down
the row.
So you get a little bit less intensity, and with that spacing.
Yeah. Because you have the sun.
But I have the sun.
Yeah.
Right.
But more closer spacing than a vegetable greenhouse would use too, right?
Yes. Yeah, much closer. Have you seen? We always go back and forth with LED light compared to HPS light, and the degradation per foot of energy of photons. Like we thought that we were seeing a greater degradation with LEDs the higher you went up compared to an HPS.
Yeah, usually we don't call that degradation. We just call that, it's called the inverse square law.
Yeah.
As you go up, the photons spread out more. Yeah. That is one of the most poorly understood laws when it applies to lighting, because it's only for a point source. And even an HPS is not a point source. It's a filament that long. It approaches a point source. But LEDs especially aren't a point source because they're spread out. So the inverse square says that the light intensity drops off by half. It's the square root of the distance to the light. That's basically what it is. But it only works for a single point source, and now you have multiple lights, and the inverse square law just doesn't apply. And because you don't have a point source. If you had a plane of lights here, an infinite plane and an infinite source, you could go 3 kilometers away and it wouldn't matter. You would have no loss of light because the photons that are going sideways still hit plants. So it depends on the focus of the lights and where the spread of the lights and where they go. Because as you go up, more photons go sideways and they miss the plants.
So what you're talking about is like kind of a perfect situation where you have a really big area and you can hang your lights pretty high up. But now when you go indoors, then
it matters.
It matters, right? And so that's what we've been thinking on is canopy penetration and uniformity for different settings and different light source types. And I always come back to I like the bars because it spreads out spatially the sources and it gives them a lot of penetration angles into the canopy, and also because it's LED you can put them very close to the canopy, so you can have you can get both high intensity and good uniformity over each portion of the canopy. So that's, but yeah, we've been having debates internally about this stuff, and it's I think it just depends on the grow situation, the setting, quite a bit.
Now, yes. Now it also starts to get less critical when you have white walls, because the photons aren't completely lost; they bounce back in, and you got to be careful about which photons are sideways, because when we talk about penetration, when you have a bunch of leaves at angles, if you gave me 2 photons straight down, or you gave me 2 photons coming in sideways, I'd pick the 2 coming in sideways, because they statistically can penetrate deeper in the canopy.
For sure.
So a lot of people think they all ought to be coming straight down, but it's just the opposite. If they're coming at angles, that's better.
Yeah.
What's up with that side light, Roach?
Yeah. Well, and if you have the bars, on our 4-foot, right, or on our 645 or our 860, you have these bars that are spread out, and the end bars have, light coming in like this into the canopy, also every other angle. So you're kind of having every angle. You're catching every angle from a lot of different starting points.
The multiple angles, that's the definition of diffuse light. If you put your hand like this and you can't see the shadow, that's diffuse light. And diffuse light penetrates canopies better than direct light.
Yeah.
One way I've been thinking about this, Bruce, and tell me if I'm wrong, but like the optimum penetration would come from a situation that's like a cloudy day but has the intensity of a sunny day.
Yes, exactly. Sometimes I thought we should put the LEDs around the perimeter and point them into the middle. In a greenhouse, that could be true, where you don't want to block the sun, so you put them on the sides, and you have laser-like focused LEDs shooting them in sideways.
Yeah.
That's our next product.
There you go.
Yeah. What do you think about LED companies or LEDs that are put in HPS form factors? So they take LED diodes and they compact it into more of an HPS style fixture.
To me, that would only be good if it was somehow cheaper or something. I guess you could argue for that if it's shaded less in a greenhouse, but this is what we're talking about. We want to get them diffuse. We want to get them spread out. The more spread out they are, the better. So concentrating them is going the wrong direction, unless there was some other advantage, cheaper manufacturing, cheaper shipping or something. But man, if you pack LEDs together, you got a heat problem. You got to get rid of a lot of heat.
Yeah, you got to get rid of a lot of heat, and it limits you because now you're stuck going at least 2 to 3 foot over the canopy.
Yeah.
Which is you're losing efficiency to the canopy. You're losing PPFD. That's why we're always focused on making the white lights wider, which is why we came out with the 860 and made a 5-foot wide light, just so we can get that closer to the canopy. We are going to work on a similar design, but only for greenhouse.
Yeah, I like the bars for greenhouse usage. I think that's a slick place where they could go in and have a lot of flexibility, and you could hang them high, you could hang them low. And I don't think that the high red's going to have a negative impact because it's going to get washed out by the daylight. But for some people who want to have that more compact style of light, we are looking at that. We have some new thermal ideas, how to manage the heat and have really good airflow across the fins and keep the LEDs cool. But there's some challenges with that because, like Bruce said, you got all the LEDs close together, they're getting hot. And there's LEDs that can handle it, but they're not the most efficient LEDs. So there's a trade-off there. You can't use the best LEDs in that setting. You can use pretty good ones, and you can make some good products, but there's just some trade-offs that you're dealing with.
Bruce, what's NLI?
That's a term that I started to coin it's the opposite of DLI. DLI is daily light integral. How many photons do the plants get in a day? But when we get to cannabis, it's exquisitely sensitive to light pollution. That's been a real active area of our study, is exactly how much light pollution can it tolerate. But one of the questions that comes up is, would a bright light for 1 hour be the same as dim light for 12 hours? And that's a thing called reciprocity. And the answer is, we don't know, but it might. And now you get to the concept of NLI, which is night light integral. Same as day. You add up all the photons at night, and if they stay below some threshold, then the plants are going to be fine. Doesn't matter when they happened, it's the integral of the whole night. So I've started to use this term to describe the effects of light at night on flowering, especially for cannabis because it's so sensitive.
You probably use the moon as like a foundation to start and start with the moon and then work your way up.
Yeah. And we have.
Okay.
The moon is as bright as it seems on a full moon night. At the peak, it's only about 2 nanomoles per meter squared per second. Nanomoles. That's 0.002 micromoles. And you think, wow, this is really bright. But if you go out with a book on a full moon night and try to read it, and you wait till your eyes are adapted, and you get a kid's book with big print, you still can't read the book. Okay. And you think, wow, I ought to be able to read this book. But it's not. You point it right at the moon. You still can't quite read it. The moon is not enough to trigger light pollution in cannabis.
Such a low diffused light, because it's almost like a diffused light, right? The moon, it's just over such a large meter, but it's such a low amount, but it's so well diffused, right?
Yeah. It's reflected sunlight.
Yeah.
And it's also not at the peak in the sky all night long, too.
True.
That's the concept
100%.
of an integral. It gets up to 2 and comes back down. But I think when we talk about light pollution, what if somebody comes on and turns on a light in the room? Is that enough to trigger it? Well, for sure it is if you leave the light on. But what if you only have it on for 5 minutes? It doesn't contribute very much to that night light integral.
Yeah.
And typically the night light integral is going to have units of nanomoles per meter squared per second. And the daily light integral will be moles per meter squared per second. Won't quite be nanomoles, I'm sorry. It'd be moles per meter squared per night.
Yeah.
Period.
Yeah.
For dark, integrated over the dark period.
Yeah. How long have you been working on that study to see what the?
Oh, a year or two for maybe a year and a half for cannabis. We looked at colors of light and their effect on cannabis at night, and of course intensity, and a little bit across different cultivars. Cultivars vary from each other for their sensitivity. One of the things we found was green light was really quite effective at inhibiting flowering. And we've always said, oh, green light, that's a safe light, doesn't trigger phytochrome and all these things. But green photons penetrate deep into leaves. And so they were just as effective as red photons in inhibiting flowering.
Oh, so all the green lights sold for night.
Yes, but our eyes see green light so well, we can use dim green light, and it's still a good safe light. Okay. If you had to choose a color for a safe light, I'd choose green. I'd just make it dim.
Gotcha.
It's not completely safe. It's safer.
Yeah.
I'd still choose green because you can see those photons so well.
I heard you're doing a lot of study beyond par or beyond 400 to 700 nanometers. Can you go into what you're working on?
Yeah, we've especially studied far red photons. And this is partly because we have a really efficient far red LED. And that's a longer wavelength. And what we've been interested in is, do those photons cause photosynthesis? Because the conventional thinking is that there's a sharp cutoff. If it's 710 nanometers, forget it. There's no photosynthesis. And there's this thing called the Emerson enhancement effect. It's the effect of far red photons on photosynthesis. And Emerson did this work in the 1950s. And it was really brilliant work. And it was in the papers, in the scientific literature. And then Emerson got killed in a plane crash, and nobody followed up his work. But now we came along with far-red LEDs, and my colleague at the University of Georgia, Mark Van Neersel, started studying these, and then he had a really brilliant PhD student, Shuyang Zhen, who worked on this, published papers, and then she came to my lab as a postdoc for a few years, and we continued to study this. And as a result of all of our studies, we now have what I would call compelling evidence that far-red photons cause photosynthesis. And that's a big deal because we always say photosynthesis is 400 to 700 nanometers. And if you're a student and you don't put that down right, if you flunk the class, well, now we think that's wrong. It should be 400 to 750 nanometers, which means we could be putting some far-red LEDs, very efficient far-red LEDs in fixtures, and still increase photosynthesis.
Are you seeing
Higher photosynthesis?
Higher
Than you would in other ranges in that 4
Well,
to 700?
one far-red photon is equal to one shorter wavelength. It's not equal. It's not like they're magic. They're twice as good. They're just equally good.
Got it.
So they should be included in the definition of photosynthetic radiation.
Yeah.
So it's you'd suggest, and I think you've talked to people about this, redefining PAR or extending the PAR definition to go from 400 to 750 nanometers.
Yep. And because of that, we call that E-PAR. It's like a lowercase e, capital PAR, extended range PAR, so that people don't get confused with the old definition.
Extra PAR.
Extra, there you go.
And just to close the loop on this, though, Apogee, do they have EPAR sensors so you can capture that input to the plants?
Yeah.
Good.
Since that's my company, I didn't bring that up, but
I think I actually just got one of those, actually. Bro. I think I got one sitting on my desk.
But yeah, those have been especially popular with cannabis growers, especially because you get a bigger number from the lights.
But let's talk about the far red too, because it has kind of specific physiological responses, right? Does it make the leaves broader? Is that one of the things?
The fundamental thing we know happens, we've known this for 50 years, it enhances cell expansion. And plants in the shade get more far red, and the cells get bigger. And so when the cells of a leaf get bigger, this is all good, really, really good. They're capturing more light. But the cells in the stem get bigger too. And so the plant gets taller. And most plants, when you get too much far red, they just get tall. And that's bad. You don't want them tall. So it's like a blowtorch. You got to be very careful about using far red photons, not to overuse them.
We're going to look at that.
What was your DLI number that you saw was too high on those far reds? Was there one that you ended up coming to, or it was like you were pulsing it or running it for however many hours a day?
Yeah, no, they were run in the daytime along with the other lights.
Yep.
And really it's a sort of a linear increase. The more far red you give them, the taller the plants. And then after that, it's what's acceptable to a grower.
So
10% taller,
could
20%
be useful in
taller.
certain situations.
It could.
It
It
could
absolutely
be.
could.
I think Bruce, you suggested kind of at the end of veg, maybe that's a good time to apply some far red.
Is it efficient on scale, though? I think is what,
I don't see any reason that wouldn't scale. The effects of far red on photosynthesis.
Even efficiently?
Yeah.
Inefficiency?
Yeah, they're pretty efficient. They're almost as efficient as the deep red LEDs.
Got it.
You're talking about the electrical efficiency.
Yep, electrical efficiency, sorry. Yeah.
Sometimes you have a choice. You could just add more deep red, right?
Yeah.
Or you could do far red.
Yeah.
And so it's not always better to just do far red because you can. You could just put more deep red in there. Yeah. Plants love it. It's super efficient. But with this physiological effect, you might want to, put that in at the right
certain
time.
Stage.
Yeah, exactly.
Certain stage,
Exactly.
100%.
They're going to be expensive. They're not mass produced like white LEDs. so that we got to be buying enough to get the price down.
They're not as expensive as UV LEDs. So
Well,
I think,
okay.
and they're much more efficient.
Could
They're
our
much
fixtures,
more efficient. Yeah.
Could our fixtures be high in, in red?
Yeah. So what we're looking at right now with some testing that's getting initiated is for the veg. We're also looking in flower, but I think veg is more promising. Is to put a little bit of far red in there to swap out a little red for a little bit of far red, just to get a little control on the plant morphology to in the veg phase, make the leaves bigger, kind of branch it out. So then you put it in the flower and you're absorbing that much more light.
Yeah, but could they already be EPAR? We're just not measuring it.
Either way you measured it, because we don't have any far red in our production fixtures, they would measure the same whether you measure it by EPAR or PAR, because we don't use those LEDs. But if you measured an HPS, right, with an EPAR meter versus a PAR meter, you'd get different numbers because they have light.
HPS has about 3-4% far red photons, and historically we just haven't counted them.
Bruce, do you think there's prospects that it would go beyond 750 nanometers? That there's photosynthetic prospects?
I don't like to answer no, but to many things, but the answer is very, very unlikely. And right from the start, we can show that after 750, they're just not absorbed. There's no pigments to absorb them. And if they don't get absorbed, they can't do anything.
I've seen some plasma lights claiming effects beyond 750, and it's like, I don't know. That seems unlikely.
They have to, if they make that claim, they have to come up with the physiological mechanism underlying their observation. And as an example, look at the huge spike from high pressure sodium at 830 nanometers. Does that do anything? No, just heat.
Yeah.
And it's a huge spike, but
Yeah.
doesn't help anything. So,
Do you think that far red in the HPS could lengthen internode spacing? So you're, like you said earlier, the plant's growing taller, but is that affecting internode spacing?
yes, in our studies it has. It's not very much, so it's not a big effect, but it's there. You can measure it.
So farther red could be having larger spacing on internodes, which kind of brings me back to metal halide and why, when growers were using HID fixtures, they used metal halide in the veg to keep them short, and then far red in the HPS because they were getting longer, lankier plants in general when they used it HPS.
Yeah.
So maybe it's the far red. Right?
Well, let me think about. It's been a while since we used metal halide lamps, but I don't think they have much far red. I'm just trying to remember that.
No, but keeping the plant short. So we came from a background. Now we're in LED and we're going towards high red, which we're getting shorter, stockier plants with that. But in the past, when we were limited to HID, we were just using metal halide, and we used metal halide to keep the plants shorter, and we used HPS because we knew they'd get a lot of stretch, and maybe that has to do, the higher red and the far red is creating that stretch.
Yeah. I think you'd be careful when your red fixtures are so much more efficient. You get higher intensity too.
Yeah.
And that intensity keeps them short.
Yep.
Granted, they still have blue in them.
Yeah.
They still have, a good chunk of blue in there to kind of keep them short as well, right?
Yeah.
Because if you were to go
10%
100% red,
Yeah.
it's almost like that. You get into that far red where they just internodal spacing is way stretched out.
But 10% blue, and
Is pretty.
that's a lot.
It's a good chunk.
Yeah,
Yeah.
for sure.
Yeah. Well, cool. What are you excited on that you're working on recently? Like, what are you like that?
Yeah.
I can't wait to go back and look at this one growth chamber that I'm doing.
Oh,
Because you've done a lot.
yeah.
You've done a lot of experiments.
Can I pick the top 3 or 4?
Yeah. Someone asked me my favorite strain. I'm like, I can't tell you that. I got
there you go.
multiple.
There
Yeah,
you go.
Yeah.
one of the things I'm really excited about is we've remodeled this big system to do canopy gas exchange. So these are sealed chambers, and there's 10 of them. It's a very sophisticated system, but it measures the metabolic rate of the community of plants every few seconds in that chamber throughout the whole day. So it's like people, how fast are they breathing now? And you turn the dials and you look at what the plant response is. And
this is for NASA, I'm assuming, for
Well,
space, because you're kind of looking at it for that chamber.
Well, in reality, NASA paid for a good part of that, but there's some cannabis plants in the chamber now, so.
Okay,
Yeah.
cool. I like
But-
that.
So
But that shows you exactly how fast photosynthesis is happening. How you're counting the exact amount of carbon dioxide
Yes.
that's getting taken up. So you know exactly whatever your conditions are, what that rate is. That's cool. I went out and I saw maybe an earlier version at your lab, and that's cool because it just tells you exactly what the metabolism is, right?
Yeah. Photosynthesis in the day and then respiration at night, which is equally important. What happens to all that carbon? It's going backwards at night, and the plant is resynthesizing other things at night,
Of course.
like maybe making cannabinoids at night.
Yeah,
How do we know they're only made in the day? They're probably made all the time.
for sure.
So it's a canopy gas exchange system.
Very cool. That sounds, I would love to see that.
And it just gives us a lot of potential to test different things. We can look at short-term effects in there, humidity effects, temperature effects, interacting factors.
Here, you're playing God. You're just playing
Yeah.
God on this chamber, right?
Yeah,
You're
and if
controlling
you,
everything.
If you want to get something that gets you out of bed in the morning, well, go in there and turn those dials and look at the lines on the graph.
For sure.
Way cool.
For sure.
Yeah.
That is cool.
Yeah, it's awesome.
And what are the other
Yeah,
one or
well,
two?
we had to pause there. I'm particularly interested in studying light pollution at night. How much do colors matter? How much does there reciprocity? What can we do with this? We know that there can be genetic selection to make plants less sensitive to light pollution at night. And one of the ways we know that is we tested soybeans are also really sensitive to light pollution in the literature from 50 years ago. So we test soybeans. They're not very sensitive at all. Well, what's wrong? Is that literature all wrong? So we called the USDA and we said, we need some of these exact same lines you were using 50 years ago. And they sent us the seeds and we tested them. By God, they were ultra sensitive to light pollution.
Yeah,
So
that's
the
the
old
thing that's
genetics-
happening with cannabis right now. You know,
yes.
some people are like, "Oh, you can do this with cannabis." It's like you can do that with that specific one.
Yes,
you know, it's
yes.
same thing as grapes and wine industry and different genetics and yeah.
Yeah. So I
Huge
think
differences.
breeding-wise, we could select away from light sensitivity, but it'll take a while.
Yeah, there's been a lot of selective breeding for higher THC and color and stuff over the past few years, and you know, some of this stuff kind of gets lost in translation. You know, down the way.
There's a lot of interest just in the whole planet in light pollution, you know,
Yeah.
dark sky movement and all that stuff.
Yeah.
But Apogee sells a light pollution sensor. And guess what? Lots of cannabis growers are buying them now to check their light pollution.
Do you think plants can see the IR from the cameras?
Really good question. So we bought some high-intensity IRs.
Yep. Because
And-
I always see it when I look at the cameras in the rooms, you see this huge. It looks like a white light over the canopy,
Yep.
and then you see it, you're like, that's the IR.
And we've recently published a paper on this. And the answer is, if the intensity is high enough, they can see it. But high enough means right next to a parking lot spotlight IR camera.
Got
You
it.
would never have that anywhere near that in a room.
Yeah.
So no, the practical answer is no. You just have to have one little plant surrounded by IR cameras. Then they could start to
Got it.
detect it.
It's all intensity.
Yes,
a lot
it's
of
intensity.
it's intensity
And
when you're talking.
That's 860 nanometer. Those LEDs.
I thought it was 850.
Okay.
But it's and then then there's a tail, and we think that's the photons in the tail that are doing it. The ones down below 800. But the quick answer, for any practical purposes, absolutely not. Don't worry about it. But
I know people wonder.
Yeah.
Well, they run around with black tape to tape them over.
Oh, yeah, yeah.
And there's circumstantial observations that the hermaphrodites next to those plants, all kinds of things. But in our studies, no, the intensity's nowhere near high enough.
Yeah, that makes sense.
Yeah.
Very cool.
Cool.
What else is on the list, Brian?
Nah, that's it. We're good.
What's
That
on
was
your
awesome.
list? What's on your list, Morgan? What didn't we get?
Oh, we touched on it, but physiologically, the green photons, what they are photosynthetic. They work. People have shied away from them in the LED time frame because they're slightly less efficient than the blue or the red. But we touched on it because they're good, so people can see what they're doing. But plant-wise, what is the plant response to green photons?
Once they're absorbed, they're every bit as good as any other color. But we physiologists brought them on themselves because we published textbooks that show absorption of chlorophyll in blue and red, and hardly any absorption in green. And so people say, well, the green photons are worthless, but they also penetrate, and they're the best color for penetrating deep in the canopy and getting to lower leaves. If you take a leaf like this, and a green photon might be 10% reflected, but it's highly transmitted to lower leaves as well, so that spreads the light out in the canopy. So that makes green photons really unique and valuable. We would use them a lot more if there was more efficient LEDs to make them.
Yeah.
But now we get them from white LEDs.
Yeah, you only get them from the phosphor conversion, which is actually pretty efficient, but it's not as efficient as just the pure blue or the pure red LED.
Mm-hmm. Yeah, I think green photons have been underrated, the value of them for plants.
Just thinking about my list here again.
Oh, no, we covered a lot.
Dude, we did a lot.
Yeah,
It was
we
dope.
covered a lot.
It was
It
dope.
was sick.
You were asking me about the interesting stuff. We really do a lot of research on nutrition, too.
I'm gonna make it up.
Lighting. So,
I'm gonna make it out there and come see you
okay,
soon.
yeah.
It's a killer lab.
Yeah.
Some I heard through the grapevine, some visiting scientist went home and he says, "Oh man, that was like the Disneyland of plant research labs." And I think he meant it because of all the colors of lights. But there's a lot of hydroponics and a lot of nutrition research going on to manipulate plant growth and plant health
Morphology.
and quality and morphology with nutrient ratios.
Oh no, 100%.
There's a lot of potential there, and
We see it as
there's
well.
17 essential elements is a lot of, so it's almost like 17 factorial possible combinations of things.
Yeah.
It's complex.
Tons of variables. Yeah.
Yeah.
Climate. All the inputs.
One of the big things on that note I'm big on is we've really done a lot of studies on phosphorus, and we could just go on for quite a bit about how much phosphorus. And I started from the standpoint if cannabis doesn't need any more phosphorus than any other crop. Well, after a bunch of studies, I realized, no, it does need more, but not way more. And people give cannabis plants egregious amounts of phosphorus. And phosphorus is a horrible environmental pollutant. That's algal blooms in lakes and rivers. So we need to use enough phosphorus to get good quality and good yield, but no more.
Without being wasteful.
Without being wasteful.
Yeah. Of course, that's what we have to do with everything. That's why, transitioning into different energies and different, efficient lighting systems and everything, everything is about efficiency now.
So having a phosphorus additive, for cannabis, I mean, kind of not necessary as much as the usual cannabis user uses.
Oh,
it.
yeah.
Well,
Yeah.
we know that because we're Athena.
Yeah.
But
I mean, you used to,
it used to like 10 mLs of liquid cool bloom, like,
yeah.
now we use zero.
Yeah.
No,
For sure.
that change is coming in the industry.
Here's what happens with phosphorus. After some studies, I could tell you. All plants pack their seeds with phosphorus to give them a good start in life. They have a concentrated phosphorus so they can germinate and start growing with a good. It's like a bag lunch for the seed.
Hence why we recommend using Athena Bloom,
Yeah,
Bloom
exactly.
and clones. Everyone always asks, like, why are you using Athena Bloom?
Yeah.
The phosphorus.
Yeah.
So now comes cannabis with no seeds at all, but a big flower, and that flower panics and it says, I am getting bigger, I need more phosphorus, even though there's no seeds. So it sucks phosphorus, and the flower gets incredibly high phosphorus, way more than it would ever need. It's just storage phosphorus. And it's such a big magnet for phosphorus, we've seen what we think is cannibalizing phosphorus out of the leaves into the flower. So at the end of the life cycle, the leaves, the phosphorus in the leaves start going down, even though we're feeding ample P, and it's all going into the flower. So the solution for us is, and everybody's just give them more phosphorus, feed the flower, so it doesn't cannibalize the leaves.
So that's what, can you explain that again? Is that why, where the phosphorus came, such high phosphorus in cannabis production, we're saying where it came from?
Yes, that makes cannabis unique. Sinsemilla cannabis, I guess,
Yeah.
without seeds. There's no seeds, so that clump of flower, which gets to be large, has a lot of phosphorus in it. And it's not used physiologically, it's just storage phosphorus.
Oh, it's not used to increase production
No.
or increase quality.
No,
It's
No.
just the phosphorus is being stored there.
it's just stored there.
Do you think that's, negatively impacts like quality, or negatively impacts people, smoking it in a certain?
No, I don't. No, I don't think
No.
it hurts anything there. It's more that it sucks valuable phosphorus out of the leaves, and the leaves have to have the phosphorus for the ATP production. Lots of things that the leaves need phosphorus for. The reason we can say that is when we take weekly samples, we see these flower buds going way up in phosphorus, and the leaves going down.
So feeding more phosphorus is sucking phosphorus from the leaves, putting it into the bud.
Well, feeding kind of feeds both leaves
Okay.
and flowers. That's
Okay.
what it does.
But-
You got so much that the flowers don't cannibalize the leaves for phosphorus.
So that's the physiological process that people understood or understand, but then it got over responded to with people using too much phosphorus.
I don't think anybody's besides us has looked at the movement of phosphorus, the translocation. What it came from was just empirical studies. If we give the plants more phosphorus, does the yield go up? And lots of people have data that, yep, the yield goes up with more phosphorus. There's evidence that's really specific to cultivars. Our colleague Narit Bernstein in Israel, she came to visit the lab last summer. She published a really nice paper at Frontiers in Plant Science on phosphorus. And if you look at her data carefully, one cultivar was a flat line. It didn't respond to extra phosphorus, but the other cultivar did. And she went up to quadruple the amount of phosphorus, and the yield was still going up. So that's one of those things where it just suggests there's a lot of genetic interaction. Some cultivars benefit from higher, some don't. But I think when somebody gets some data, a heritage grower gets data that phosphorus helps, they just give everything high phosphorus, and real high, like an order of magnitude higher than the plants might really need.
Yeah. Cool. Oh, to finish off, Morgan, you're working on some projects. How many spectrums you got in the pipeline that are going to Jungle Boys?
It's six, I think. So we're just looking at, so Bruce and I talk and I read his papers and see other papers and I'm pretty convinced we have great spectrum that are optimized, but I still want to ask Roach to try out some UV to see if see what it does firsthand in a production environment during the flower cycle, and then looking at some far red with our R80 spectrum, taking out some of the red and putting in some far red to see how it affects the morphology of the plant. Because when you walk into a production scale study like that, and you have the kind of the A/B study, the two different treatments, and you walk in there and you can see right away what's the difference, right? We make a pretty modest adjustment to the spectrum, and Roach can walk in there after a few days and be like, whoa, this is good, this is bad. And then if it's kind of in between, that's where we have to dig a little deeper. So we're looking at a bunch of spectrum, blue, UV, far red, that are added on to our basic spectrum now. And then we're looking at some booster bar stuff, which gives you like a little added flexibility.
Yeah. Are you doing UVA, UVB?
Not doing UVB because those LEDs are so inefficient that to provide a dose, you have to use a lot, right? And then it's not good for people to be around. Now that's kind of manageable, but I don't want to be giving people sunburns, and the LEDs don't last very long, so they kind of degrade super quick. So I think that's a case where I'm not sure that it works, and even if it worked a little bit, I'm pretty sure it's not worth it. So that's where we're at. But that said, we made some extra special products that have never been made before and gave them to some researchers, including Bruce, to see what they can find out also.
Sounds fun. Right on. All right, Bruce, really appreciate you. Yeah,
Thanks. Been fun.
Yeah, it's good hanging out today. Roach, thanks. I know you got a lot going on.
All good.
Morgan, appreciate
Dope.
you.
It was great to be here.
Yeah. Thanks.
Been wanting to get this guy in here for a while.
Yeah, it's awesome. Appreciate you guys.
Thanks, Morgan.
See you.
Thanks for
Thanks.